Hello, a very warm welcome to this video. So in this video I'm going to be sharing with you a nice kind of series for the convergence of kind of the value pi. I'm going to be showing you how to kind of quickly derive pi if you need to find the series and have kind of forgotten what the value is or what it might be, because this series converges very nicely. And so I thought I would share with you this because it is useful in terms of understanding maths to play around with these kinds of things. And also it's very satisfying to find an infinite series which converges to a number like pi. And I have shared with you the equation we are essentially deriving towards on the screen. So the equation essentially says that pi divided by 4 is equal to the limit as n goes to infinity of the sum of the terms 1 over n squared minus k squared to the power half, where the sum is going from k equals 0 to n. And you can approximate pi, because this expression is exact, but you can approximate it by saying, well, pi, you get pi or pi over 4 when we take a large, if not infinite, value for n. So this is the kind of equation we'll be deriving. So to begin with this, we have to define what we mean by pi. Well, a good way to define pi is the area of a circle which has a unit radius. If you think of the formula for the area of a circle, if I have a unit radius, the area of such a circle equals pi. And I can split this circle, which has a unit radius, into 4 parts. We call it splitting it into the 4 quadrants. And each of these kind of quarters of the circle, because they're all even, they all have kind of the same portion allocated to them. Each of these segments is going to have an area of pi over 4. The area of the circle as a whole is pi, and so the area of one of these segments is just going to be pi by 4, because we have 4 of them, and when we put them together we have the circle as a whole. So that's a good definition for pi, or pi over 4. Now we then say we can approximate the kind of area of the circle in one of these quadrants by essentially, instead of considering the circle as a whole and then dividing it into 4, we consider a series of rectangles, and rectangles are easy to calculate the area of, because the area of a rectangle is just its width times its height by definition. And so kind of by summing the area of these rectangles, we can approximate the area of a quarter of a circle, and therefore by summing these rectangles we can approximate pi by 4. And when we have an infinite number of rectangles and the width becomes infinitesimally small of each rectangle, then the approximation becomes exact. But kind of for the purposes of visualization, I'll be dealing with non-infinitesimal rectangles, so rectangles which have kind of a macroscopic width, and therefore this equation is approximate. So pi by 4 is approximately the sum that we get when we sum all these rectangles, and n is the kind of the number of rectangles we're summing. Well, strictly n is an upper limit, because we're saying that the first rectangle is denoted by k equals 0, the next is k equals 1, the next is k equals 2. So strictly we would have n plus 1 rectangles, but as n gets very big, the difference between n and n plus 1 is negligible. And as we can see, the rectangles get smaller and smaller as you go along the x-axis. So the so the last rectangle is going to have a tiny width, and height, and therefore it won't contribute much to the area. What will contribute much more to the area if all these rectangles have equal width is the initial one, because we can see from the diagram that has the biggest height. And so the first terms in the sequence, which allow us to approximate pi by 4, will be the most significant, which will mean that this series will converge quickly. And so we can quickly see from this diagram, not only do we have a way of approximating pi by 4, but we have a sequence which will converge very quickly. And again, just to emphasise, K is a label which allows me to talk about a specific rectangle. So the first rectangle is the K equals 0 rectangle, then it's K equals 1, K equals 2, all the way up to K equals n. Now, the next job, and really the main bulk of this derivation, is to essentially calculate the area of the kth rectangle. So to calculate A subscript K. And I'll be summarising what I've shown on the screen here. So we have n rectangles, or n plus 1, because we're starting from K equals 0 as opposed to K equals 1. But as I say, the distinction between n and n plus 1 is small when n is large, and in the limit where n goes to infinity, the distinction is entirely negligible, and so we can just say we have n rectangles to keep things simple. Each of the kind of rectangles will have equal width, and remember we're dealing with a unit radius circle, and so the smallest value x can take is 0, and the biggest value it can take is 1. Because it structures out to x equals 1, the circle, and therefore the width, if they all have even width of each rectangle, is just going to be 1 divided by the number of rectangles, so it's just going to be 1 divided by n. So that's the width. The next thing is to calculate the height. Well, to calculate the height, we're going to use the equation for the circle, which is based on Pythagoras' theorem. But for this, we need to know what the x value is of the kind of vertices of this rectangle. So I'm talking about the kind of edges of the rectangle where the rectangle connects with the x-axis. So the kth rectangle is essentially going to lie between an x value of k over n and the x value of k plus 1 over n, because k over n is at the start of the kth rectangle on the x-axis, and k plus 1 over n is the start of the other, and thus the end of the rectangle we're talking about on the x-axis. So the rectangle is going to lie between x equals k over n and x equals k plus 1 over n. And now we've got the value of x for the kth rectangle, we can calculate the corresponding value of y. So we use Pythagoras' theorem, which essentially defines the rectangle, defines the circle. I won't be going into too much detail of this, but the equation for a circle of unit radius, which is given essentially by Pythagoras' theorem, is just x squared plus y squared equals 1. I won't worry too much about knowing the derivation for that. The important thing is that this is true for our purposes, although I'll leave the derivation out of this explanation, because it doesn't add much to the explanation. But that's the equation for the circle, and basically what that does is it describes all coordinates on the circle. So for any pair of coordinates, x and y, on a unit radius circle, they will satisfy the equation x squared plus y squared equals 1. And then essentially we substitute in our value for x to find the height of the rectangle. Now there's a question of, do we use x subscript k or x subscript k plus 1 for the height of the rectangle. Now, because the kind of equation for pi over 4 is in the limit where n goes to infinity, the rectangles become infinitely thin, and therefore the distinction between x subscript k and x subscript k plus 1 becomes negligible because the rectangle is infinitely thin. And for large values of n, the distinction isn't very important when we're just finding an approximation. And therefore, for simplification, I've used x subscript k, though you could use x subscript k plus 1. You'll come up with a different approximation. It will result in the same thing in the limit that n goes to infinity. But for simplification, I'm going to use x subscript k to find my height of the kth rectangle, which is given by y subscript k. And when you substitute x subscript k into x squared plus y squared equals 1, so you substitute xk for x to find the equation for y, or in our case y subscript k, so the height of the kth rectangle, you end up with y subscript k equals 1 over n, lots of n squared minus k squared to the power half. Wherefore, a reminder, to the power of half simply means square root. And now we can find the area of the kth rectangle, so that's just the product of the height and the width of the rectangle. The width is 1 over n, the height is given by our equation for y subscript k, and therefore the area is as shown on the screen. And essentially the value of pi over 4 is then just the limit of the summation of these areas as n, so our upper limit for the number of rectangles goes to infinity, which is essentially the equation here. So I hope this has been helpful. I've tried to keep this brief, but this is a good formula for kind of calculating pi quickly. It converges because the informant terms and the initial terms as described above. You can also use it to calculate pi to a high degree of accuracy if you kind of, write this into code and quickly get it to calculate a sum in the limit of a very big value of n. And this equation is exact in the limit when n goes to infinity. I really hope you've enjoyed this video. It has been hopefully helpful in learning about how we can go about finding an estimate for the value of pi and writing pi as the limit of a convergent sequence with an infinite number of terms. I hope this has been enjoyable, and please check out my channel for more.